name is Sven Seuken. I'm the session chair. And it's my pleasure to introduce Chara as our first speaker, who will be talking about strategy-proof linear regression in high dimensions. The floor is yours.
Good morning, everybody. I am Chara, and I'm here to talk to you about strategy-proof linear regression in high dimensions, a joint work that we did with Yiling, Chen, Ariel, Procaccia, and Nisarg, Shah. Allow me first to introduce to you the notion of robustness to, clicker wasn't working. Yes. Allow me first to introduce to you the notion of robustness to strategic noise. Normally, in machine learning, our algorithms learn by studying the relationships that govern the training data that we feed them. These training data are normally perturbed by noise, either random noise or adversarial noise. And while random noise might seem a much easier scenario to handle, adversarial noise is a much, much harder one. And that's because the adversary's sole purpose is to sabotage our algorithm. The game theory and mechanism design literature gives us an interesting middle ground, strategic noise. Under strategic noise, the agent will perturb the data set up until the point that their losses surpass their gains. And to make this slightly more formal in our model, our agents today will control one data point. The xi's, the independent variables, are going to be publicly verifiable information. The yi's are private manipulable information for each agent. The agents are going to be strategic in the sense that they might misreport, and they have single peak preferences. There is one outcome that they prefer above all, and they want this outcome for them. We, as principals, we want to construct linear regression mechanisms by taking as input these reports and learning the true relationships that govern the data. An example of such single peak preferences you can see in this graph here, where agent I is extremely happy when the line passes directly through him. He doesn't care about anything else, just about the fact that where the line crosses the line x equals xi. And he becomes more and more disinterested as the line moves further away from him. An example of scenarios in real life where such models appear is whenever the data that we collect come from surveys where the agents know that their reports are going to be used in the future, and they do not want to be perceived as real outliers because that will have some economic effects in the future. The desiderata for our mechanisms are that we want them to be strategy-proof and group strategy-proof. And of course, we want them to be meaningful in the sense that somebody will tell me that, of course, y equals 7 is a line that is obviously strategy-proof, but tells me nothing informative about the underlying data. And we also want to establish strategy-proofness and group strategy-proofness without the need to impose monetary transactions. And before I move on to the higher dimensional setting, I'll give you an example of what a strategy-proof linear regression looks like in 2 dimensions. In the higher dimensional setting, I would like to define a new mechanism that is for group strategy-proof high-dimensional linear regression through the use of the Ham-Sandwich theorem. And before I move to the higher dimensional setting, I will give you an example of what a strategy-proof linear regression looks like in 2 dimensions. This family is called the CRM family, short for clockwise repeated median, was defined in 2004 by Perote and Perote-Peña. And just a disclaimer here, the original family was wrong. We showed why it was wrong in our paper. We established the corrected result, and here I present to you directly the corrected result. Assume that we have the data set on the right, then the mechanism, the first step, is to split the data set into 2 subsets, S and S prime, such that either S and S prime are equal or they are separable. In this example here, I'm just going to focus on them being separable, which means that in 2 dimensions, there has to be a vertical line separating the 2 sets, S and S prime. Now, we compute from each point in S towards points in S prime the median clockwise angle. And what is this angle? Let's start from this point here. We compute the clockwise angles from 12 o'clock, so towards points in S prime. So this is the first angle, this is the second one, this is the third one. I choose the median of those angles towards points in S prime. Therefore, among three angles, the median is the second one. I do the same iteration for the second point and the third point, all the points in S. And then from these median clockwise angles, I choose again the median. So the median of the medians. Again, with respect to the 12 o'clock, I'm counting the angles. So this is the first one, this is the second one, this is the third one. So this angle here is the median of the median clockwise angles. And now the output line is simply the line that connects the 2 points that share this angle, 1 point from S and 1 point from S prime, always for this mechanism. And let me just ask you this question, because this is how our thought process was for this paper. How would you generalize this mechanism into higher dimensions? In the interest of time, I will just reveal to you that the hardest part when you start thinking about these questions is how would you encode angles in higher dimensions? What do angles mean in higher dimensions? And there are other problems, but I'm hiding them under the rug right now. With respect to the angles, we found a much nicer way to represent this family. And we termed this new family generalized resistant lines. They have a much nicer and much more analytical description. They are lines that are parameterized with two sets, S and S prime, which we choose with respect to just the publicly verifiable part of the data set, and two scalars, K and K prime. And now, what is the output line? The output line is simply the line that makes the kth minimum residual from set S equal to the K prime residual of set S prime, equal to 0. What is a residual? A residual is the difference between the reported variable, so this portion here, and the predicted variable that our output line will create. An example of such residual mechanisms you can see in this data set here, which is exactly the data set that I had before to analyze the CRM family. Now, the two sets are separable with respect to this line, so S and S prime. And I've chosen the second minimum residual from this set and the second minimum residual from that set. The second among three is, of course, the median residual. And this explains also the name that our mechanism has gotten. The median residual was defined around 1950s in the statistics literature. They are called resistant line estimators, and they were defined as alternatives for the ordinary least squares mechanism that was not robust to outliers. They were robust to outliers. That's why they were defined. We generalized this family, and we showed that not only the resistant lines, but also any percentile, like for example this one, where I have the first minimum residual and the third minimum residual for these sets, the respective sets S and S prime, are group strategy proof. And as I hinted before, this family, the previous family, the CRM, the corrected CRM, is engulfed in full in this family. And while that might seem straightforward for the case that S and S prime are separable, it wasn't straightforward at all for the case that, for the full CRM essentially, when S and S prime are equal. And now let me come back to the question that I asked you before, and I claimed that the hardest part to answer was the angle part. How would you generalize this mechanism now, which contains the whole previous family? It is group strategy proof, but still it is in just 2 dimensions. What is the hardest part to make that transition? Again, in the interest of time. If I close my eyes and I just directly generalize that to higher dimensions, I would do the following thing. Instead of just 2 sets, I will define D plus 1 sets. Instead of just 2 scalars, I will define d plus 1 scalars. And now, instead of making the median residual from the two sets equal to 0, I will make the kth minimum residual from each set equal to 0. Are we done? The answer is no. And it's actually pretty tricky, because this is what I hid under the rug before. I hid under the rug the separability part. Observe that in this equation here, we knew exactly that this equation has unique solution always because of the fact that the two sets that I've chosen, S and S prime, are separable with respect to just a vertical line. In higher dimensions, however, this is not so straightforward. It's very tricky to define good separability conditions that can guarantee that this solution here has unique, this equation here has unique solution. And this is where, in fact, the connection with the Ham-Sandwich theorem came into play. Cartoonishly portrayed, the Ham-Sandwich theorem in 3 dimensions tells us the following thing. If you have those 3 dimensions, bread, cheese, say it's ham, I couldn't find a better picture, and bread again, then there always exists a simultaneously bisecting cut for all 3 dimensions. What do I mean by always? No matter how you place the bread, no matter how you change and slice the ham, there's always an appropriately tilted hyperplane that can bisect all these 3 dimensions. A bit of background here. It was originally defined by Stone and Tukey in 1942 for continuous measures and just for bisecting hyperplanes. A discrete version of the above was defined in 2011 by Eldon and Hill. This is all literature from computational geometry, by the way. Still bisecting. The discrete version told us that when you have discrete set of points, there's a hyperplane that leaves half of the points of each set above and half of the points of the set below of the hyperplane. And while that might seem to get very close to what we would actually like for our separability and making the median, the minimum residuals equal to 0, it still lacks, it still has 2 problems. The first problem is that all these results just captured the existence, not the uniqueness. In fact, in more than once, you can have many bisecting hyperplanes. And also, they just capture the bisecting hyperplane. What we would like ideally is to have a mechanism that tells us that, look, if you want me to leave 1/3 of this set above the hyperplane, 2/3 of the second set below the hyperplane, 5/5 of the 5/5 of the third set above the hyperplane, this is the hyperplane that you need to define. So we should capture other percentiles apart from the bisecting hyperplane. And Steikler and Dow in 2010 came very close to what we would like to have. They defined some good separability conditions that guaranteed that they could have uniqueness and also hyperplanes that dissect any percentile, essentially. And again, observe right now that this still is a problem almost purely stats. That is not, I haven't even considered my game theoretic desiderata right now. I'm just trying to generalize a statistics mechanism, a statistics estimator. And what do the separable sets look like? In their example, intuitively, well-separable sets, if you look at this picture from above, and this is a three-dimensional picture, then well-separable sets are sets that any said subset of these sets is separated by the remaining sets by a hyperplane. So for example, if I choose this set here, then there exists this hyperplane that separates it from these 2 sets. If I choose these 2 sets as a set subset, then this hyperplane here separates them from that set here. And an invalid set, and a set that would make these well-separable sets invalid would be if I had some sets in the middle. Why? Because then very simply, the 2 sets in the 2 pockets right here, there does not exist a hyperplane that can separate these 2 sets from this middle set here. Were we done? Did I define separability? Well, kind of. For our purposes, we wanted to define separability just with respect to the publicly verifiable information. So once we were able to define the separability with respect to just the x-axis, which is the only information that we have publicly for the agents, and we also relaxed some of the conditions that Stigler and Zhao needed, we could guarantee now that this equation here has not only unique solution, but also our game theoretic desideratum of group strategy proofness. And while it might seem crazy in higher dimensions, I will show to you why this is not so crazy by the proof sketch of the two-dimensional line. Now, I have changed my data set a little bit, and I've chosen the median mechanism. Under truthful reporting, if you actually take some time, you will realize that that is the line that is created. I call regions A, B, C, and D with respect to this vertical line and where the output line is. And then I claim that in any coalition, when any coalition of agents deviates, they create a new line. This new line creates new regions, A prime, B prime, C prime, D prime, and there exists at least one region that is a strict superset of a previous region. So in my example, forget about where exactly the points are. Some points deviated and they created this line here, the pink line, okay? These are my new regions. And now region C prime is a strict superset of region C. And this, I claim that this is all that I needed. Why? Because C prime, okay, C prime has n4th points. Why? I have separated the sets into half, and I've chosen the median, so n4th approximately points, okay? Region C prime, now region A also had n4th points, but region C prime has more than n4th plus 1, at least n4th plus 1, and region A prime has at most n4th plus 1, thus creating an imbalance. So there's no way that this pink line could be created by a median mechanism. And that was all that I needed. And just very briefly before I close today, I'll just mention a couple of other results that we have included in the paper. We showed that we generalized previous results by the L1 ERM being group strategy proof. That was work by Dekel et al. We showed that contrary to what I tricked you into believing today, not all strategy proof linear regressors are group strategy proof. And we created a new family which we called impartial mechanisms that are strategy proof but not group strategy proof. We showed that we showed necessary and sufficient conditions for a linear regression to be strategy proof, and also we showed that no strategy proof linear regressor is 2 minus epsilon efficient compared to the ordinary least squares, which is of course not strategy proof. And finally, a couple of open questions that stem directly from our work: whether there exists a constructive characterization of all strategy proof linear regressors, and whether we can find the most efficient strategy-proof linear regressor. Thank you. Yes?
Can you compare a little bit Moulin's characterization?
Yes, thank you. So our result, our characterization is closely mirrors the characterization of Moulin, because our characterization says the following thing. From the perspective of each agent, if I forget about all the other agents, then from the perspective of each agent, what essentially we have is that there's an upper and a lower bound, which closely mirrors the phantoms that Moulin has, such that the output line that I see as in x equals xi is always the median between my report, the lower bound, and the upper bound, which is a kind of direct byproduct of Moulin's mechanism when you just have two phantoms and one report. So there is this nice connection, and in fact, we even tried to get, I have the final the question about the constructive characterization. We even tried to generalize the phantoms for getting a constructive characterization, but it didn't seem to work. So that's why we think that is an important question. Yes?
What's the complexity of computing in a GR8?
Oh, that's bad. So solving the bisecting ham sandwich theorem is PPA complete. It's a paper that was uploaded on arXiv late May. So I don't think, like, if you are happy with some trivial well-separable sets, like saying I just want one point to be separated, then it's fine. You can compute it very fast. But otherwise, if you want meaningful well-separable sets, then it's not efficient.
Okay, thank you very much.
Thanks.
And